So let's talk through this example that we have here. We're going to be looking at the 2013 NFL season. In that season, the home team won 153 of 245 regular season games. And what we want to see is this evidence of a home field advantage? That the home team, if we think of this as a sample, should make that our sample proportion right there, they won 153 out of 245 games, which in terms of a decimal would be 0.6245. So if the home team is winning 62.45% of the games, we want to see, is that an actual advantage? And what we need to see is it statistically significant? Yes, this is a high percentage, so it shows that there might be a home field advantage, but is it significant enough to officially say, yes, this is what's happening? So finding evidence is going to be kind of ambiguous for a little while, and then we'll talk about the exact way to know whether or not we have evidence from our sample statistic. So what we want to see is this landing close by or is this landing far away based on our assumption? And our assumption is going to be that there is no home field advantage. So if our proportion is representing this proportion of games won by the home team, then under this assumption that there's no home field advantage, what we're really assuming is that this proportion is just 50%, 0.5. The idea being that there's a 50% chance the home team wins versus the away team. And in this example, we're kind of excluding the idea of skill and how teams are ranking. It's just talking about an advantage based on where they're playing, 50-50 chance of who wins. So as we can see, if we're assuming that this proportion should be 50%, our sample shows 0.6245, which is definitely higher than the idea of 50%, this no home field advantage. But we can't really tell is it's larger, but is it landing here in terms of this idea of no home field advantage? Is it lining up close enough that it isn't really evidence of it being significantly larger? Or is it this scenario where, yes, under this assumption of no home field advantage, we have this extreme result, which would start pushing us into this evidence of there is a home field advantage. So this first step that we're going to have in these hypothesis tests is to set up these hypotheses. In the hypotheses, we want to describe our assumption and what we want to prove. Describing our assumption, that's going to be our null hypothesis. And we denote that with this capital H with a subscript of 0. And this is what we assume is true. It's going to be some baseline value, or like this, it's that idea of 50% means there's no sort of advantage. There's going to be something described where it's going to be kind of our baseline that we want to prove against. And then our second hypothesis is going to be the alternative hypothesis, which we denote with this capital H with a subscript of A. And this is what we want to prove. So for us, our assumption is this idea of no home field advantage, and what we want to prove is that there is a home field advantage. So for us, writing our null and alternative hypotheses, this is what we want to bring through. For our null and alternative, our null, we want to be describing this idea of no home field advantage. And then in our alternative, what we want to prove is that there is a home field advantage. So to bring through these two ideas, while we can describe these hypotheses in words, really we want to bring it into notation and numerical values. So as I wrote up here, our assumption's at 0.5. So how we would write our null hypothesis is we'd say our null is P equals 0.5, meaning if we have some population proportion, we're assuming it's 0.5. What we want to prove is that if there's a home field advantage, that this proportion is actually higher than that number of 0.5. So what we want to prove is that if we have this population proportion, it should be more than 0.5. So this is what our null and alternative hypotheses should look like. In general, what you'll see coming through for the null is the proportion equals and then some number, some baseline value that we're assuming to be true. So in the null hypothesis, you'll always have the equals sign there. In the alternative, there's a few different forms. We still want to talk about P. You always want to compare it to the same numerical value. So whatever number's in the null hypothesis goes in the alternative. Or if you can kind of put together the alternative first, whatever number's there goes in the null hypothesis. But then the symbol that we put in the middle here, there's three options. We could be trying to prove that the proportion is more than, or less than, or not equal to. And this is just going to be based on the wording of the problem. So for us, because we're trying to show an advantage, that means we need to increase this proportion. If we were trying to prove that maybe the home team loses more of the time, that there's kind of this like a home field disadvantage, then that would start to switch it to the less than, that we'd want to see this proportion be less than 0.5. And then sometimes we just say we want to show that it's different. We want to say that it's not really an advantage or a or rather, this is kind of tricky with this one, but usually it's just that the proportion's different. And with that, we bring through the does not equal sign. So this is our general form for the null and alternative hypotheses. And for our example, this is what's set up. So we always want to state these because it tells us our assumption and what we want to prove. So from this, we set up kind of this idea of what we think is happening in our population, and then we want to see how our sample compares. Is this sample giving us evidence to prove this alternative hypothesis, or is it not giving us evidence? So that's where we end up with these two scenarios, is that this would be the case that we don't have evidence for the alternative, and this is where we do have evidence for the alternative. And we just need to know, where is our sample landing? So to decide if there is a home field advantage, we need to determine a certain probability. And it's this idea of, we have our sample data, what's the probability of it occurring underneath this null hypothesis? This distribution should all be built around the null hypothesis being true, and what's the probability of seeing these sample results? So for us, it's going to be the idea of assuming that there's no home field advantage. Meaning assuming that our proportion is this 0.5. So assuming that's true, what is the probability of seeing our sample results? Seeing a sample statistic. And then what's going to be happening, as we talked about with the normal distributions, we can't find the probability of an exact value. It's just, with the normal distributions, the probability is always an area under the curve. So what we end up doing is finding the probability of the sample statistic or more extreme. So like for us, it's the idea of what's the probability they won that many games or even more games. So it would be the probability of seeing a sample statistic as extreme or more extreme than ours, than our sample proportion. So what this is going to look like, especially for our example, is that we build a distribution around the null hypothesis. So this is the idea of assuming the null hypothesis is true. So for us, it would be the idea of assuming that we have that 0.5 as our population proportion, where we have this sample statistic of 0.6245 landing somewhere over here. I don't know if it's all the way out here in the tail. I don't know if 0.6245 actually lands right here. That's where we need to know more about the distribution and specifically the spread of it. but I'm just going to go kind of vague of, let's say it's landing right there. The probability we're interested in is what's the probability of landing at that value or even larger than that value. This area under the curve, this is what we want to find. That's going to tell us if we have evidence or not. Because if it's landing way out in the tail, we're going to be having a small probability of seeing it occur. And if there's a small probability of the sample statistic under this being true, that starts giving us evidence for this. But if we have this case where it's landing pretty close by, that's going to create a large area, which means there's a high probability of seeing that result if this is true. Which means if there's a high probability of seeing it, if this is accurate, then we're not really getting evidence that our proportion's actually larger. So that's where we need to see, is this probability small or large? Something we're going to be doing in our calculation, instead of working with this distribution, is we're going to change everything to the standard normal curve. Meaning that distribution that's normal with the mean of 0, standard deviation of 1, which means we're going to change everything into z-scores. Which means if it's the idea of landing on our assumed population proportion, that's going to come through as 0. Then what we're going to do is create a z-score for this value, and we're going to end up calling that our test statistic. So wherever that's landing, it's going to land in the same spot, just under this different distribution. But we want to find this z-score, and then under this distribution we can find the probability of that value or more extreme. So it lands similarly, we'd get the same probabilities. It's just going to be easier to work with this curve rather than setting up our sampling distribution. It ends up being all the same, but it's more consistently used in our steps. So we kind of look back up here, moving to our standard normal curve, it's that this would become 0, and then it's that we're going to get these different test statistics out. And then it's going to be a matter of, is our test statistic landing far away and creating this small area? Because then we have extreme results, and that's showing that our population proportion is false. Or is it landing close by, which if we created an area with a z-score that's close by, we'd end up with this big probability, which means we don't have extreme results. There's a high likelihood of that occurring under our assumption, so we can't say our assumption is false. So this is what we want to get at, and this is where we're going to get our evidence once we find the area here. So that's going to be the next video, is going through the actual calculations.